So this whole project stems from the following question, is that, how do I go to the previous one? There you go. Is that we want a nice category of complete topological modules. And this is connected to some work in condensed mathematics, which I'm not going to talk about today because we can actually phrase it very separate from that. So just as candidates, we are going to start with profinite vector spaces, which its objects are infinite products of a field. And then the hom from this infinite product into K, you get that sum. What this means in particular, this equality, is that you should think of that product as some sort of topological product, because these points sort of stuck together. And now any map like that factors through a finite subset of I. So it's some sort of like compact product. And if we want to do geometry on this, well, we do kind of the most reasonable thing, which is we do the category of ultrasolid modules is the shifted co-completion. Ignore the word shifted, you're freely adding co-kernels and sums. And that way we have an abelian category on which we can finally do homological algebra. So for example, there's a completed tensor product on it through which if we take formal power series on X and formal power series on Y, we get formal power series on X and Y. And notice that this doesn't happen with the usual tensor product of algebras because you can only take finite sums of elementary tensors. An example is if you take R, a complete local Noetherian K algebra with residual field K, then we can write it as this inverse limits. And now the Noetherian hypothesis forces each of these quotients to be a finite dimensional vector space. And in particular, this is a profinite vector space. So the idea is that any such algebra, given it like the topology coming from the maximal ideal, we can consider as some kind of ultrasolid algebra. And we can generalize this kind of behavior. So a complete profinite ultrasolid K algebra is essentially the same as before. So we're going to ask for something that is complete and local with residual field K. And instead of asking for Noetherian, we ask that the underlying space is just a profinite vector space. So for example, the example I mentioned before is any complete local Noetherian K algebra with residual field K with the appropriate topology. But then also we can take formal power series in infinitely many variables. So we allow, for example, an infinite sum of distinct monomials. So that would be such an example. Now, after telling you about all this ultrasolid stuff, I'm going to take a little detour and tell you about deformation theory, because that's the main application I found of this so far. And the idea is if we take a smooth proper variety, we want to understand deformations of it. What do we mean by this? So if we take a local Artinian K algebra with residual field K, so what this means is that in particular, it's a finite dimensional K vector space. So we should think of it as some infinitesimal thickening of K. So a deformation of X is a variety over spec K such that when we now recover K points, it's X. So we should think of this as a deformation of X in a way that is consistent with the deformation that is A of K, okay? And all of this makes much more sense in the language of higher geometry. So it's a world where we replace rings with simplicial commutative rings or infinity rings, choose your favorite. But the idea is some sort of algebra where we can do homotopy theory in a meaningful way. And we can talk about homotopies between maps. And we can generalize this kind of deformation problem. So the idea is that before, I give you an Artinian ring, and you can return sort of the space of deformations over that Artinian ring of your variety. So more generally, a formal moduli problem would be a functor, and I've intentionally avoided saying what that is, but some Artinian algebras, but derived version of, into the category of spaces, because then again, we're working in the world of higher geometry, so the space, or rather homotopy type of deformations, might have paths, and a path would signify a homotopy between two different deformations. So it is something such that deforming over K, which is the base field, should just give you the point, because there should be no non-trivial deformations over the already existing base field. And it also preserves sets and pullbacks. And it makes sense to think about this in terms of scheme theory, because if you dualize this, right, deforming over a pushout is just deforming over each of the pieces in a way that agrees in the intersection. So that is essentially what we're asking for in here. And the main theorem, this paper came out, I think, 2 weeks ago in the archive, is that a formal moduli problem is co-representable by one of these kind of generalizations of these Noetherian algebras, if and only if the space of first order deformations, so deformations over the dual numbers, is discrete. In particular, this means that there's no sort of weird homotopy business going on here. So it's just like an honest set of points rather than a homotopy type. And the idea is to keep exploring the future in this, I currently have in mind applications in Galois theory, deformation theory, and group cohomology, but those are all ongoing projects. Thank you very much.